Hello everyone, my name's Jordan Pattee, and I'm going to be presenting the paper Intelli-dynamic Malware Detection Based on Processor Behaviors, written by myself and Byung Lee from the University of Colorado at Colorado Springs. So here is our roadmap for the talk today. The first thing I'm going to do is give a background on why we were interested in researching hardware-based malware detection, followed by the methodology that we use in our experiments to collect the data and then classify between malicious and benign samples, followed by the results of our experiments, and then the analysis of our experiments with the key findings, followed by the conclusion, and that will wrap it up for today. So there are a few different reasons behind our interest to research hardware-based malware detection. One of the first things we noticed was the change in total malware instances reported annually. From 2011 to 2020, there was a change of reported instances from 65 million to a little over 1,000 million reports. And this is alarming because the cost to clean up a single incident reported by the US government is around $1 million. And both organizations and individuals are harmed in terms of privacy and financial means as well. Additionally, existing software-based malware detectors are slower than hardware-based malware detectors, and they tend to rely on signatures. And due to obfuscation techniques by modern malware attackers, child malware samples can actually be generated from parent malware samples. So then we also begin to see an exponential growth in the number of signatures that exist. And because these signature-based software detectors rely on databases of signatures, it becomes very difficult for them to obtain all signatures generated from a parent malware sample. And then one problem with the existing hardware-based solutions is that they use hardware performance counters, which we also use in our experiments, but they use an unrealizable number of them. So most modern processors have anywhere from 4 to 8 or 4 to 12 hardware counters that monitor hardware events such as CPU cycles, instructions retired, and branch information, as well as cache information. But because they use too many of these counters, it makes the data seem a little bit too optimistic. And then one other thing that we want to look at is different feature representation. We do use machine learning for our classification of malware versus benign samples. And because of that, we wanted to look at different data representations. So instead of using a single representation of data and testing on multiple models, let's try to see if we can transform the data into different types of representations and see if we have an increased accuracy for classification. Now I'm going to go over the methodology that we use in our experiments to collect the data and in the end classify between malicious and benign applications. So one of the first things that we had to do was create a safe environment that allowed us to execute the malware inside of while preventing the host computer from contamination. We decided to go with Linux containers, and one of the benefits of a container environment is that a user has access to the actual hardware components. So we had access to the real hardware counter readings, whereas a virtual machine would emulate these readings. So we believe that the accuracy would be improved by using a container environment. Our malware samples we obtained from virustotal.com, and they also have a hash lookup. So they gave us a Linux executable malware directory, and we used those hashes from the samples in the directory to identify the malware families that were included, which were rootkits, trojans, worms, and viruses. And for our benign samples, what we did was also run applications inside of the container just so that we had the constant environment. And we ran applications such as Python scripts, web browsers, including Firefox, Chrome, Internet Explorer, and then music players as well, and other applications, gaming applications, so that we were able to collect data for benign or harmless applications. And the way that we are able to access the hardware readings was using perf tools provided by Linux. And using perf tools library, you have access to around 40 different hardware events. And because we mentioned that some papers use an unrealizable number of counters, such as 30 when only a few exist on actual microprocessors, we decided to use the worst case scenario, where you would only be able to monitor 4 events at any given time. So given the 40 events, we were able to divide into 10 batches of 4. And so we monitored 4 events at a time for 30 minutes, and that gave us a total of 5 hours per malware sample of data. And the reason we decided to have such a long sampling period was due to the fact that we were noticing long periods of dormant behavior, meaning that we would have a reading of 0 accesses for the malware applications. And as we increased this time of profiling, we noticed that there would be a spike maybe after 10 minutes where then we would begin to see hardware readings. So we were also looking at this amount of time to characterize behavior of the malware samples. And from the data, we were able to do 2 different forms of feature representation. The first thing that we did was take the sum of the total accesses over the 30 minutes for each individual counter and consider that as the feature. And then you would be starting out with 40 features, each with a different sum. And then the other thing that we did was make time series plots, which we converted into images to feed into a CNN, a convolutional neural network, to see how the classification compared using the image-based method versus using the numerical-based method. So the next step that we had to take was feature selection. Feature selection is a common practice in machine learning where you remove redundant features, as in features that don't contribute to classification from your data set. So we started out with 40 features, and we used the Weka software for data mining to reduce those 40 features down to only 5. And inside of Weka, they have multiple different evaluators, which are algorithms that perform feature selection, such as Pearson correlation, for example. We did multiple tests on different evaluators and used the built-in classifier to see how the initial performance was. And we found that this CFS subset evaluator was the best for our data set. And one of the key details behind this evaluator is that it looks for features that have low intercorrelation between each other, but high correlation to the prediction class, which is exactly what we wanted. We didn't want to have redundant features, especially when we were dealing with hardware. And then we had those 2 types of feature representation that I mentioned, which were the sum of total accesses and time series images. After feature selection, the next step was to do the actual classification for the malware and benign samples. In this project, we were doing binary classification, meaning classification only with the 2 classes, malware and benign. So we don't do a multinomial classification on the types of malware in this project. And then, as I mentioned, we are using 2 types of feature representation. The time series images were fed into a CNN, and then the other classifiers, which I'll show in a table in a second, used the sum of total accesses as the features that I mentioned earlier. Here, table 1 shows the hardware events that remained after feature selection using Weka, which were CPU cycles, hardware instructions, cache references, cache misses, and branch instructions. And then table 2 shows the classifiers that we use in experiments. For the CNNs, we actually propose a custom malware model, which is why we use 2 baseline models, the first of which is LANet5, which has an architecture closest to that of the model we propose, which is why we use it as one of the baselines, and then the other one is VGGNet. VGGNet has small kernel sizes of 3 by 3, and we also implement that same kernel size, which is why we chose VGGNet as a baseline. And then for our other classifiers, we just went with general classifiers that are commonly used in machine learning. We also wanted to include ensemble learners such as random forest and AdaBoost. And then the other 2 are logistic regression and multi-layer perceptron. Now I'm going to go over the results from our experiments. So the first thing that we did after we collected our data was characterize the malware samples from the benign samples, where we had two notable observations. The first one being that the malicious applications tended to have long periods of inactivity during the 30-minute sampling period, where the counter readings were 0 during this time. And this can be shown in figure 1 on the left, where that inactive period is circled. And what this implies is that during this time, malware may go undetected by hardware-based detectors, and that in order to capture the actual behavior of the malware sample, we need to be profiling for a longer time than this period of inactivity. And then the other thing that we noticed was that the magnitude for the number of accesses between the malware samples and the benign samples were different. So we took the average for all of our samples and we found that the average CPU cycles, so this is just one of our features, the average CPU cycles was close to 16 million for benign applications, whereas malware applications tended to have average CPU cycles of around 26,000 for the counter value. Therefore, using these two observations, we're actually able to show that there is a distinguishing factor between the malware and benign applications, and that implies that we should be able to classify between them using machine learning. So I mentioned earlier that we propose a custom malware CNN in our project, and that the architecture is closest to that of LeNet 5. So the main difference between our architecture and LeNet 5's is that we have one additional layer, and that our activation shape is smaller than LeNet 5, which leads to fewer parameters, and that's because instead of using a 5x5 kernel size, we're using a 3x3 kernel. So here is a visual perspective of our proposed CNN framework. So similar to traditional CNNs, we have a combination of convolutional and max pooling layers before a fully connected layer. An important note is that our input images were 28 by 28 pixels, which is rather small, but we wanted to sacrifice the resolution of the images since they're only graphs for the computational efficiency in the hardware. Here we have the classification results for our proposed malware CNN versus the baseline CNNs of LeNet 5 and VGGNet. We use the diagnostic tools called precision recall curve and receiver operating characteristic curve to evaluate the performance of the models. Generally, precision recall curves are better for unbalanced datasets, and receiver operating characteristic curves are better for balanced datasets, but both give meaningful insights to the performance. So here we have, on the right-hand side, we can see that for the precision recall curve, our malware has an area under the curve of 0.99, where 1 is considered perfect classification. And then on the right-hand side, for our receiver operating characteristic curve, we have 0.98, indicating a 98% accuracy for our model. And we can also see that our proposed model outperforms both LeNet 5 and VGGNet. So in addition to comparing the malware CNN that we propose to the other baseline CNNs, we also wanted to investigate whether or not the feature representation from the same dataset would influence the classification rate. So we compared our CNN, which was fed the input images, to general classifiers that were fed the sum of total accesses over the 30-minute sampling period. And those classifiers again were random forest, logistic regression, AdaBoost, and MLP. And from the precision recall curves and receiver operating characteristic curves, we can see that in addition to our CNN, the ensemble learners, random forest, and AdaBoost perform exceptionally well, where in the best case, random forest was able to classify with a 99.2% classification accuracy. Now, an important note is that as datasets grow, we can assume that this classification accuracy will decrease a bit. So that's just something to keep into consideration. In analyzing our results, we were able to come to some key findings. The first one was that our proposed malware CNN was able to outperform the baseline CNNs in terms of area under the curve for both the precision recall curve and receiver operating characteristic curve. This is an important detail because it shows that CNNs can be tailored to be very application specific, and we added a single layer and changed the kernel size from len at 5, and we were able to achieve a 18% accuracy in the worst case scenario. So this is a motivation for users to make sure that a CNN is tailored towards their image input. And then the other thing that we found is that our ensemble learners, Random Forest and AdaBoost, performed the best in terms of AUC overall for the classifiers, and they were using the sum of total accesses from the hardware performance counters as features. And what this implies is that feature representation actually does play an important role in a classification model. It's important to make sure that the classification model has the data represented in a way that the mathematical model is going to be able to learn to classify optimally. And then, as far as the malware goes, we were able to identify that there's a large period of sparsity for the number of accesses of the executable malware compared to benign applications, and also the low magnitude of the actual accesses allow us to classify between the malware and benign applications using machine learning. So to wrap up for today, the big takeaways from our project were that the hardware performance counters available in microprocessors can be used to classify between malicious and benign applications. And we did this using a realizable number of counters, which was 4. And we were able to accomplish this by using batches of events rather than trying to increase the number of hardware counters themselves. And then one notable observation about malware is that malware tends to have periods of inactivity, the sparse behavior. And in order to accurately characterize the malware, there should be a profiling time long enough to capture the actual behavioral period where the spikes in counter accesses begin to happen. And then also, the proposed CNN and ensemble learning classifiers yielded classification accuracies above 96%. In order to increase this accuracy, we could experiment with the model design and also feature selection, maybe using a different feature selection method or manually implementing the method would be able to boost that accuracy. So for future work, we plan to implement our models on physical hardware. And then we also want to continue exploring different data representation types and continue to understand whether or not that can improve the classification rate. Thank you very much for your time.